Relative velocity. If we're on a motorway, we're traveling in a straight line, and we're in a car, we might be traveling at 10 meters a second. But sometimes you can hear the motorbike coming behind you to overtake you in a straight line, and he might be traveling at 30 meters per second. And if we translate these into vectors, this will be 10 in the I direction, and this will be 30 in the I direction. So we can call this the velocity of the car. And we put an arrow over it for our vector is equal to 10I. And the velocity of the motorbike is equal to 30I. So after 1 second, you can see the motorbike, after it passes, it's going to be 20 ahead, and after 2 seconds, 40 ahead, and so on. Now we can translate this into the velocity of the car relative to the motorbike. And the velocity of one object relative to the other is the velocity of the first one minus the velocity of the second one. So the velocity of the car relative to the motorbike is equal to 10I minus 30I, which is equal to minus 20I. So this is the car is falling 20 behind. If we do it the other way around, the velocity of the motorbike relative to the car is the velocity of the motorbike minus the velocity of the car, which is 30I minus 10I, which is equal to 20I. It's gaining 20 per second. So let's have a look at this in relation to, these are just single vectors in the I direction. Let's have a look at vectors in the I and j direction. In this example, if we take the velocity of the car again, we'll do car and bus this time, but it doesn't matter what they are. If we take the velocity of the car is I plus j. In 1 hour, say after 1 hour, the car is here. And the velocity of bus as 2I minus j. After 1 hour, the bus is down here. So they're moving in different directions. So if we take the velocity of the car relative to the bus, it's going to be the velocity of the car minus the velocity of the bus. Line them up over each other. I plus j, the velocity of the car, and minus the velocity of the bus is minus 2I plus j. And we're going to get minus I plus 2j. And if you see here, if we take our vectors here, this is at 2 and this is at 1 on the x-axis, and the change in x is 1 or minus I. And in the j direction, it's at 1 and minus 1. And you can see the change is 2, which is what we have here. What about if we move these on a little bit? And we move them on maybe from another, what if we multiply this vector by 3? So 3 hours is 3I plus 3j. And in 3 hours, this one will be at 6I minus 3j. So 3 plus 3, approximately here. And 6I minus 3j is approximately here. Now we multiply a vector by a real number, it's just going to stretch it out from the origin. So here and here. So if we look at the velocity of the car relative to the bus, the velocity of the car minus the velocity of the bus, it's going to be 3I plus 3j minus 6I plus 3j. So we're going to get minus 3I plus 6j. And let's just look at our vectors here. We're at 6 here. We're at 3 here. So you can see the change is 3 in the I direction. And we're at 3 here. And we're at minus 3 here. So you can see the change is 6 in the j direction. The first example, we're going to say ship A is 500 kilometers due west of ship B. And ship A is traveling at 10 kilometers an hour in the direction 30 degrees north of east. So let's just do a little sketch here. If we'll always put one of them at the origin. So ship A is west of B, so A and B. Ship A is traveling in north 30 degrees north of east. So ship A is traveling along this line here, 30 degrees in this direction. So that's positive, positive. Remember our vectors chapter. So A, the velocity of A is going to be equal to the speed, which is 10, by the cos of the angle times I, and it's positive, positive, so it's 10 times the sine of the angle in the j direction. And 10 cos 30 is 10 by 3 over root 2, and we'll decimalize it here, 8.66 in the I direction, and sine of 30 is a half, 5 in the j direction. Now collision course is the second part. The j's will have to be the same if they're on a collision course. So we'll look at that now in a sec, but let's get the velocity of B first. B is here. It's traveling, just change colors. It's traveling in a direction northwest, so 45 degrees at 5 root 2. So it's approximately going in this direction here, 45 degrees. So that's negative, positive, just always double check these. So the velocity of B is equal to 5 root 2 by the cos of 45, and that's the negative one, plus 5 root 2 by the sine of 45. Sine of 45 is 1 over root 2. So this is going to give me minus the root 2's will cancel. Minus 5 in the I direction, which I left out here, and plus 5i in the j direction. And we're asked for the velocity of B relative to A. Don't forget your arrows. So that's going to give me 8.66 in the I plus 5 in the j. And underneath I'm going to write minus velocity of B, which is 5i minus 5j. So in this case, we're going to get 13.66 in the I direction for the velocity of B relative to A. There's no J. Just written down the wrong way. That's A on top, so it's going to be, change the size around, minus this one, plus this one, minus this one, and minus this one. So it's minus 13.66. So let's look at B here. Showed her on a collision course. So we call this the relative position. You remember from vectors of B relative to A is 500 kilometers. And that was up here. This was this 500 up here. So that's 500 in the I direction for the relative position of B relative to A, or the position of B relative to A. So to show her on a collision course, what we say is, since the velocity of B relative to A, which is minus 13.66 in the I direction, is equal to minus k times the relative position. Don't forget your arrow of B relative to A. In this case, k would have to be a positive constant. So that's equal to 500 in the I direction. So you can see here the time taken. Time is going to be the distance over the position. Sorry, the speed. Or the relative distance over the relative speed. So these will collide at 36.6 hours. So relative displacement, when we have two vectors, or three vectors in this case, if Oscar is at the origin here, is done exactly the same way as velocity. We can see here A is at the number 3 here for I. B is at the number 1. On the J we're at a 2 and a minus 3. So you can see here the change in j is 5 and the change in I is 2. So let's just have a look at this in mathematical terms. Just connect up our lines here. So we write it as the OR of A. So the relative position of A relative to the origin is 3i plus 2j. The relative position of B relative to the origin, or the position of B relative to the origin, is I minus 3j. 3j. So the relative position of A relative to B is equal to the relative position of A minus the relative position of B, which is 3i plus 2j minus I plus 3j, which, as we said, the difference in the I was 2 and the difference in the j was 5. So let's have a look at the first few exercises in 4a in relation to these questions. Okay, so a few easy ones to start this chapter. An automobile traveling on a straight road at 25 meters per second. We'll call this A. The velocity of A was written by an American. An automobile is equal to 25 in the I direction. It's overtaken by a bus traveling 30 meters per second in the same direction. So the velocity of the bus is equal to 30 in the I direction. Find the velocity of the bus relative to the automobile. Velocity of B relative to A is going to be the velocity of B minus the velocity of A, which is going to be 30 minus 25 in the I direction. I should probably just put them in. So that's equal to 5i. And our units are in meters per second. And you can see how long they're going to be. For 1 kilometer apart, well, he's gaining 5 per second, so 1,000 divided by 5 in 200 seconds. They'll be a kilometer apart. Question 2, A and B. I'm going to just simplify these down now, these questions. A and B start from the same point. Velocity of A is 4 meters per second. The velocity of B is 7 meters per second. Find the velocity of B relative to A. Velocity of B relative to A is the velocity of B minus the velocity of A, which is equal to 7i minus 4i. If we create the vectors, which is 3i meters per second. How far apart after 60 seconds? Well, 3 by 60 is 180 meters. And after how long will they be? 600 meters apart. So time in this case, so we'd have 3 by t is equal to 600. So you can see that t would have to be after 200 seconds. Now, question 2, 3, and 4 are similar. So I'm going to jump up to, or question 3, 4 are similar. I'm going to jump up to question 5, where we have 2 parts to the vector. Question 5, we're given the velocity of P and the velocity of Q, and we're asked to find the velocity of P relative to Q. So the velocity of P relative to Q is the velocity of P minus the velocity of Q, which is equal to 5i plus 2j. You'll put the minus here if you want, and then just put the vector in itself, minus 2i minus 2j in the bracket. So coming down here, we're going to get 5i minus 2i, 3i, and 2i minus 2i plus 4j, which is the velocity of P relative to Q. Now the magnitude of this is going to work out evenly here. You can see the answer already. The square root is 3 squared plus 4 squared, which is 5 kilometers per hour. And I should have put that in as well for my units here. And after how long will the ships lose visibility? Well, at the side of each other, the visibility is 20 kilometers. So you can see here, after 1 hour, 5, 2 hours, 10, 3 hours, 15, 4 hours, 20. So 20, the distance that they can see each other divided by the speed that they're going at is going to give me time, 4 hours in this case. In question 6, it introduced the direction now, so we're asked for the magnitude and direction of both of these. So number 1, the velocity of A relative to B is equal to the velocity of A minus the velocity of B, which is equal to 4I minus 3J, and underneath I'm going to write minus the velocity of B minus 6I plus J, which is going to give me minus 2I minus 2J. In meters per second. The magnitude of this is equal to the square root of 2 squared plus 2 squared, which is equal to root 8. Or you could write it as 2 root 2 if you wanted. And the direction we'll call the tan of theta is always the j component over the I component, which is equal to 1. So in this case, theta works out to be an even 45 degrees. Direction here, so we have the angle. Now let's look at just the sketch of the vector. It's minus 2I plus 2J, or minus 2I minus 2J, so it's going this way, minus minus, and we have a 45, so it's going southwest, directly southwest. The next one is the velocity of C relative to B, so 6I minus J, velocity of C relative to B is equal to the velocity of C minus the velocity of B. So what have we got? We have 6I minus J, 6I minus J, and we have 8I, so minus 8I underneath. Have I put them the wrong way around? I have put them the wrong way around. It's 8I first. C first is 8I. And then minus B, so minus 6I plus J, minus 6I plus J. So that's going to give me 2I plus J. The magnitude of this, you can see the answer is going to be root 5, 2 squared plus 1 squared, which is root 5. And the direction, the tan of theta is equal to 1 over 2. Which gives me just over 26.5 degrees, 26 degrees. I'll change that to minutes, to 34 minutes on a calculator. And the direction here, it's 2I plus J, so it's positive, so it's going in this direction. 2I plus J, this is theta, so it's going northeast. So it's going to be 26 degrees, 34 minutes northeast, or we can write that as east. 26 degrees, 34 minutes north. Question 7, you're told take O as the origin and the position vectors A, B and C respectively are the following. Relative position of A, 4I plus 2J, minus 3I plus 6J for B, and minus 4I plus 2J for C. And write in terms of I and J the relative position, or the displacement of B with respect to A and the displacement of C with respect to A, and then which is further from A. So we need to get the magnitude of them. So number 1, the relative displacement, or the relative position of B with respect to A is the position of B minus the position of A, which is going to be minus 3I plus 6J. And then minus 4I minus 2J. That's going to give me minus 7I plus 4J. The relative position of B with respect to A. Now the magnitude of this is the square root of 7 squared plus 4 squared. 49 and 16 is root 65. Okay, part 2, the relative position of C with respect to A is equal to the relative position of C minus the relative position of A, which is going to be minus 4I plus 2J, and then minus 4I minus 2J, which is minus 8, and that's just going to give me minus 8I. For the relative position of C with respect to A. The magnitude of this, you can see, When we only have one position in the vector with I and j, it's the square root of 8 squared, if you want to write it like that, but we can just write 8. And which is further from a? Well, 8, and this is just over 8, so this one here, b, has to be further from a than c.